distributed optimization algorithms. Okay. All right. So, well, the buzzword these days are machine learning or artificial intelligence, and you probably heard a lot about these. And so what is the common theme there, right? We have a lot of data. We have improved hardware capability to process these data. And we want to somehow coordinate this processing among different pieces of hardware to eventually solve a problem. Okay, so I'm going to abstract the system and say there are a few pieces that I'm going to focus on. One is these systems can be modeled as a large-scale network, meaning it's a network of processors somehow connected to each other, and they have access to local information, and each of these processors has some kind of local processing power. Okay, so I'm just going to abstract it at this level. And I will give you an example what this may entail. But for now, let's see what are possible applications. Okay, so if you have a computer cluster or a cloud that has many processors in it, that fits the bill, right? It has a lot of different processors that each has access to its own hard drive with local information, and then it can do some processing. And wireless communication is yet another one where you're trying to relay the information, or you can think about this network of cell phones, and the popular topic these days is federated learning. So you can think about, you have an iPhone and it has Siri on it. Somehow it's training itself to recognize what you're telling it. So how does that work, right? So each of the phone has a local model and can have access to whatever you're asking Siri. And then it communicates some information to the cloud. And then eventually it builds a pretty good model and doing voice to text recognition, right? And then it processes the data afterwards. So that's another example where we have local information, local processing power, and there's a little bit concern of privacy. I'll get into that in a little bit. But for now, let's move on to another example, multi-agent cooperative control and coordination. So this is another project that we have that's ongoing, recently funded by NSF. We're going to build and program a bunch of robots with distributed optimization algorithms for them to do certain formation controls. Okay, and then we also have sensor estimation. Okay, so let me be a little bit more specific and give you a motivating example. This is a very, very small scale toy example, but hopefully it'll motivate the scenario that I'm studying and why I want to design distributed optimization algorithms. Okay, so here's the setup. Let's say we're in a city and you have N sensors around collecting data. And what you are interested in is to study the correlation of temperature and electricity consumption. Okay, so electricity is one of the other topics I'm very interested in. So let's say I want to build a model to predict the demand. Okay, and so I'm going to do the baby version of supervised passive learning. So I'm just collecting data. Each of these sensors is sitting there collecting data of each of these neighborhoods or whatever the nodes may represent. Could be a household, could be an aggregated neighborhood, could be a larger area. Okay, and let's say it collects data on the hour for a whole year. So that means 8,700 more data points per node. Okay, and so I'm collecting the temperature T and the consumption or demand D. So the input is T, output is D, and I'm trying to fit a model that connects from T to D. Okay. All right, and why do I do that? Because if you ever read literature about electricity consumption, the key thing the grid is trying to do is to match demand to supply, right? And so in order to do that, they need to predict the demand pretty well. And one of the key predictor for the demand is the temperature. So this is a very reasonable thing to do. I want to build a good model to map from temperature to demand, okay? And let's say after collecting data, I got back my data, and it kind of looks like this. Okay, so this is actual real data from New England ISO, and the y-axis is demand, the x-axis is temperature. So the blue dots is coming from one sensor, the red diamonds coming from another sensor, and the black square is coming from a third sensor. Let's say, just for illustration purposes, I have these three groups of data. Okay, and remember they were collected at different sensors, right? So in the previous slide, you have these go back. You have this network of sensors. They are locally collecting information. Okay, and these red lines represent predetermined communication topology. So anything that's connected by a red line can talk to each other. But for instance, this node cannot directly talk to this node. Okay. All right. So now let's say after I aggregate the data, I look at it and I say, looks like I can fit a polynomial of maybe degree 3 to describe this model. Oh, and in case you are curious why it looks like this is coming from the Boston area, where a lot of the heater are gas powered. So, and it gets pretty hot in the summer. So when the temperature gets high, like above 90, you see a big spike coming up in terms of the electricity demand. And when the temperature is low, when it's below 30, you also see the temperature, the demand tends to pop up, but it pops up less severely compared to the AC part, because all the ACs are electricity powered, but not all the heaters are. Now that's why it looks like a tilted parabola. So we may need to go up to degree 3. Okay, let's say we have decided that we want to fit a third degree polynomial to this model. Okay, so what we're going to do is to build this model right here that maps from the temperature T to output demand D. So finds this function D of T, right? So then we study this and say, oh, gee, actually, we are only interested in learning 4 parameters of the model, the coefficients, these x's, right? Even though we just said every node, if you just collect 1 point per hour, you're going to collect 8,000 per year. And let's say you can collect it for every household and maybe on the 5-minute scale. So you can be bombarded with a lot of data just for this very simple problem. And you can have, of course, more than 3 sensors in the system. But so you can have a lot of data, a lot of agents trying to fit the model collectively. But what you are interested in learning is just something in R4, right? It's just these 4 scalars that we're trying to learn. Okay. So collectively, I want to build this model that predicts this red line right here, right? That can fit the all the data collectively pretty well. Okay, so I can form the system objective. Let's say I'm doing a least square fitting, and I can put these T's into this A matrix, form the feature matrix, and then find the X, that is the parameter we're trying to learn of the model, and the D is the one we're trying to output. So these are all pretty standard setup for empirical loss minimization. And then we notice we can write the system objective as a summation of 3 pieces, right? So once we know a model, we can evaluate on each of these subsets of data based on each node, and they will give you a loss. And we want to minimize the summation of loss across the system. Okay. All right. So this is one example of to illustrate the need to run distributed algorithms. Okay, so why do we want to run distributed algorithms? So we have very, very large scale data set, meaning this AI and DI can have a lot of them, right? And so far I'm just doing polynomial of degree 3, but you can make fancier feature vectors here, okay? But what we are interested in is something low dimensional, okay? So we're interested in something in R4, okay? So if communication is costly, right? We do not want to have all the sensors communicate this data back to the cloud and run some central algorithm that has access to all the data at the same time. Okay? So communication cost could be an issue to motivate why we want to process the data locally. And you can also imagine the iPhone example I was just talking about, right? So you're talking to Siri and you may or may not want Apple to know what exactly you're telling Siri to do. So privacy is another issue. You may, because of that, you may not want to have all your data sent back to a central cloud. Okay? So all these are reasons why we want to keep the data local. Okay? Once we keep the data local, and because we are working with processors or sensors that have local processing power, they can just process the data locally and then communicate with their neighbor determined on the topology that we saw on the previous page. Okay, so that is what I mean by distributed optimization. So collectively, we're trying to minimize some kind of loss function, and we're doing computation locally without exchanging the data or the original loss function f's. And we are also only communicating with local neighbors. There's no central cloud to do the processing. Okay, and so that's a separate example right here about federated learning. And these days, the mainstream federated learning literature uses this kind of setup. So it has an aggregator on top, that's the cloud, and then it has a bunch of workers on the lower level. So you can think about the cloud being the Apple company's cloud, and then the iCloud, and then these local nodes being your iPhones that is collecting data or collecting information regarding the Siri usage. Okay. So this has a slightly different topology than the one we were talking about before, right? So the one on the previous page has this very spread out topology. It's mostly peer-to-peer. Everything is equal. It's just sensors there. They're going to talk to each other and work with each other. Whereas in the federated learning, we have this slightly different topology where you have an aggregator on top and then a bunch of workers on the bottom. So as far as I'm concerned, I'm going to consider this as a special case where we're going to restrict our attention to a star network. So this is just going to be a special case for the work I'm going to talk about today. And the method we develop should be applicable to the federated learning as well. So for that reason, I'm not going to talk about this case separately. Okay. All right. So let me now bring in the hammer and introduce the formal representation of the problem. Okay, so we are going to consider an undirected network, and I'm going to stick with undirected network for this talk. And I should say there are this generalization of our method that can work with directed networks. You just have to use the push sum algorithm to modify these undirected network-based algorithms. But okay, so I'm going to focus on the undirected one. And we have n agents. They are cooperatively trying to solve this problem here. Okay, the first one up here. Okay, so they're trying to minimize summation of fi of x. So you can think of these fi's as local loss functions. And this x is the common parameter, like from the learning model, this x would be the four scalars, the four coefficients that we're trying to learn. So that x is common to all the agents going from I to n. Okay, and so in the federated learning, the star graph, one of the aggregator may have fi equal to 0, but you can still add up all the loss function for the entire system, and every agent would have to agree on one x in the end. So just the worker would have fi that's non-trivial, and then the aggregator would have a trivial function up there to optimize. Okay. And each of the function fi is locally known only to agent I. As we were saying, this could be motivated from communication overhead or privacy concerns. Okay. And then distributed algorithm will be performing local computation and also local communication. Okay, so all the results I'm going to talk about applies for Rn, like the R4 motivating example we're talking about, but sometimes due to notation complication, we might want to just restrict our attention to xi in one dimension. It makes our life slightly easier to think about. But everything generalizes, and for instance, the first step we're going to do is we look at the problem that I put in the blue rectangle here. So this problem, once we want to solve it distributively, what is the first obstacle here? Well, Fi's are locally known, fine, but X is shared among all the agents, right? So how would the local agents have access to something global? Right? They don't. So what they could do is to make local copies. So every agent I makes a copy of xi, and if the x is originally in R4, then each of these xi is also in R4. Okay, so you copy down the whole vector. And then we are going to require, as long as I and j are connected in this topology, xi is going to be equal to xj. Okay, so I'm going to add a bunch of these local constraints. I have my local copy, and this local copy would have to be equal to all my neighbors. Okay? And if the original graph is connected, then this is the same as the problem up there in the box. All right, and this is a very standard trick to use to reformulate the problem. Okay, and feel free to raise questions in case I'm breezing through my slides too fast. Okay, so let's see. Okay, and then let's make a few assumptions. So these f's are going to be twice differentiable. I'm going to stick with the convex case here. We have some ongoing work that works with non-convex problems. So let's say they're nice. So mu is strongly convex and has L-Lipschitz gradients. Okay, and the agent knows Fi and will be in charge of updating these xi's. Okay, so essentially, if I'm agent I, right, I know my own Fi. I have a copy of xi, that's my local copy, and also I have my local neighbors I'm going to talk to, and I'm going to make sure that my copy of xi is going to be equal to their own local copies. Okay, so that's my local view, right? And if you have a federated learning setup, you have an aggregator and then a bunch of workers. Then, so it is a star graph. You can run the algorithms we have here, but if you want faster convergence, you should use algorithm specializes for federated learning case because it can use the topology properties of the star graph. So for instance, here, if I am a local agent, I only see part of the graph, right? There's no way for me to see all of the graph. Therefore, even if I can guarantee I'm equal to my local neighbors, I don't know if the entire network has reached consensus or have all x's equal to each other. Whereas if I am the federated learning, if I'm the aggregator agent, I can see the entire graph. So it is fairly straightforward there to reach consensus. Okay. So that's the main difference between these two different topologies. Okay. So I'm going to work with the general one for the rest of the talk. And what else did we do? We rewrote the constraint. So this is coming from xi equal xj type of constraint. And I'm just going to put in a matrix representation. So this A is the adjacency matrix that has ones and minus ones to make sure the two neighbors connected are equal to each other. All right. So what are some common approaches, right? So before I tell you what we're going to do, let's see what is out there already. Okay? And as we already said, each of the agents knows its local function, knows its local variable xi, okay? And it's going to try to minimize its local objective function and also trying to maintain equality with its neighbors, right? So it essentially has two tasks. Okay? So the natural thing to do is to say, hey, I'm going to every time, so I'm going to run an iterative method, starting from some value, some initialization, and every iteration, I'm going to take a weighted average with my neighbors. Okay, so to force consensus eventually, but I'm not going to make it all equal. I cannot because I can only control my local variable. So what I could do is to make this local variable be equal to a weighted average of my neighborhood. Okay, and then also I'm going to take a gradient or negative gradient step to descend in my objective function value direction. Okay, and that's exactly what this method is doing here in red. Okay, so this W matrix is represents a network topology. So WIIs are the diagonal ones should be positive, and WIJs can be positive when I and J are connected to each other, and WIJ will have to be equal to 0. when I and j are not connected. So when they cannot talk, you cannot take weighted average with that particular neighbor. And S is the step size, D is the gradient or subgradient. Okay, this method here in red is known as the distributed gradient descent. Okay. All right, and this is the plain vanilla version of the algorithm, right? It has two objectives: minimize loss function and reach consensus with neighbors. So it's going to try to combine these two modules together. And this method works. In particular, if you tune the step size so that it's diminishing to 0, this method can solve the original problem. Okay? If you stick with a constant step size, it goes to error neighborhood of the original problem. Okay, so what's good about it? It's very simple, right? Very easy to implement. What's bad about it? It can be really slow if you want exact convergence, or you don't get exact convergence. You get a reasonable speed, but you go to error neighborhood. Okay. All right, and the picture down there illustrates how information spreads in the network. Okay. So at case iteration, when we start the case iteration, let's take the yellow node in the center. At that point, the yellow node just knows its local information there. Okay. Now, after one iteration, because it would have taken weighted average with its neighbors, so it would have heard from these blue nodes right here. All right, so this is what happens. How much information the yellow node knows. It knows itself and also knows things from 1 degree neighbors. Okay. I'm just going to repeat the process. Everyone's only going to talk to its immediate neighbors. But for the next iteration, because these blue nodes also have done the same thing, they have heard from the green nodes, right? So in 2 iterations, effectively, the yellow node in the middle would have heard from all the colored nodes, including the green and the blue ones. Okay, and this is how the information spreads in the network. I'm not saying after one iteration all the blue nodes would equal to the yellow one. Okay, so there's a difference. They are not going to reach consensus right away, but they would have heard from their neighbors. Okay? So they would have to iterate still to reach consensus in the end. But at least as far as information spreading is concerned, it heard from all of these neighbors, the 2 hop neighbors, and then in 3 iterations, it would have heard from 3 hop neighbors, and so on, and it kind of grows and spreads to the entire network. Okay? And also vice versa, right? So the blue nodes would have heard from the yellow one in 1 iteration, the green node would have heard from the yellow one in 2 iterations, because this is undirected. Okay. All right, so that's one method, attempt number 1, distributed gradient descent. Okay, and we said it's nice and easy, but can be slow. Now let's try another approach. Okay, so this is the ADMM-based method, alternating direction method or multiplier-based. It's augmented Lagrangian-based method, essentially. Let's see. Okay, so I will not spend the time to rewrite the original problem, but let me tell you on the high level what's going to happen. Okay, so we can reformulate the original problem into something that's suitable for this ADMM, and what does ADMM solve? So classically, it solves this kind of decoupled problem with 2 variables x and y. They're decoupled in the objective function, but coupled through a linear constraint. So for the problem that we are interested in, we can also reformulate by introduce auxiliary variables to make sure we also have separable objectives and also linear constraint. Essentially, the linear constraint is going to correspond to different edges. Okay. All right. And then still on the high level, what does ADMM do? So once you have the objective function, you're going to form the augmented Lagrangian function. So the first 3 terms are the regular Lagrangian function, f and g from the objective function. P is a dual variable here. So the second term here is the dual multiplied by the constraint violation. And then the last term here, this one, is a quadratic penalty on constraint violation. Okay, so the first 3 terms is the standard Lagrangian. The last term is the extra penalty to penalize for constraint violation. That's why it's called augmented Lagrangian. Okay, once you have the augmented Lagrangian, what this method does is it takes 2 minimization steps. So it has 2 variables, x and y, right? So it fixes y, optimizes over x, and then takes the newly updated x value, fixes x at that value, and updates for y. Okay, so and then once you are done with the x and y, the primal variable updates, you go ahead and update the dual variable, use the regular dual gradient ascent. Okay, so once again, what does it do? It has two primal variables. It fixes one at a time and it minimizes the other. So it goes back and forth between x minimization and y minimization. That's the name, alternating direction. And then also it has a dual step there, so method of multiplier. That's why it's called ADMM. Okay. So what's nice about this method is, relatively speaking, it converges pretty fast. Okay. Compared to the previous step. Why? Because it has a minimization step built in at every step, right? So we would, I guess, you would believe me when I say for some problems, this ADM converges very fast, okay? And then what's not so good about it is also the fact that it has a minimization, actually has two minimizations per step, right? What does that mean? That means you're solving a pretty complicated problem at every iteration, right? So this, so remember what we are minimizing here. We're minimizing augmented Lagrangian, and once we fix one of the variables, obviously the problem simplifies a little bit. So for instance, in the x step, we don't have to worry about the g term. We're just minimizing the f term. But we are actually minimizing a function with respect to f, okay? So this minimization step can be pretty costly. All right, so that's the pros and cons of this augmented Lagrangian-based method. You're typically going to run a minimization per iteration, and then typically the method converges reasonably well, and also it's flexible as far as step size is concerned. So this beta here is a step size. And the guarantee for ADMM says it converges for any positive step size beta, whereas the distributed gradient method on the previous slide, we would have to diminish step size, so step size becomes an issue there. Okay, all right, so that's my quick summary of two well-known distributed optimization methods that can be used to solve the problem that we have set up. Okay, now let me just quickly go over the literature on this topic. Vaguely, I can classify them into these categories. We have primal methods, which are gradient-based, that can be slow, and then dual-based methods that are related to the augmented Lagrangian type. They need minimization per iteration. They can be fast, but the computation complexity is high, so the overall speed may not be very. So when I say fast, I'm counting only the outer iteration. And so the outer iteration number may be slow, but every iteration requires a minimization. Okay? And then we also have fancier version of Newton-based method that has a second order, uses second order information, and those methods tend to be fast, but the computation complexity is once again high. Every time you would have to solve a linear equation related to the Hessian, which is not a diagonal system, and solving that becomes complicated. So typically there's another inner loop to just solve that Newton equation. Okay, and then lastly, we have asynchronous method based on one of those three previously listed categories. Okay. All right, so what are we going to do, right? So it seems like there's plenty of methods out there. Why am I still studying this? Okay, so remember I said the two keywords on the title page are flexible and robust, right? Okay, so what is missing in the literature? Well, each of the papers I have shown you on the previous slide gives you a specific form of algorithm that the authors propose and analyze to show convergence, and they also have some simulation to support how well it performs. But there is a prescribed form of the method. Okay, what we want is a class of methods that is flexible in the following sense. Okay, so remember I've motivated the problem on a very abstract level, saying, we have a bunch of nodes connected, they can exchange information, they have access to local loss functions. And I went through a bunch of different examples, ranging from high performance computer being each of the nodes, to iPhones, to robots, right? So these different applications, different hardwares would call for different kinds of methods. What do I mean? For instance, we're talking with robotic hardware engineers, right? They would tell you, we have we have a Raspberry Pi on board, so it's pretty powerful in terms of computation power, but we don't have that big a battery on board. Okay? So you better be careful when you design your algorithm so that I don't run out of battery very soon. And also the robot, they are depending on the communication protocol they use. Communication can be very costly. So and also I'm very patient, so I can't wait for my robot to finish the task because I just send it out to do its task. As long as it finishes, I'm happy. But it should not run out the battery and needs me to go and rescue it, right? Okay, so in that setting, I don't really care about speed. I care that it finishes its task before the battery runs out. And in particular, they're saying the computation is cheap, but communication with neighbors can be costly because it consumes a lot of battery. Okay? And same thing with your iPhone example. So there is not exactly a battery concern, but rather you want to preserve the data locally, right? So you don't want all your information to be sent back to Apple. Ideally. So there you also want to maybe control the amount of communication going back and forth between your phone and the cloud. Okay. And then on the other hand, we have these supercomputers, right? So there we are talking about a bunch of cores sitting next to each other. Maybe they even have shared memory access, right? So what is hard for them typically is the gradient sampling. So they're typically the FIs are, so the loss function is representing data information from a lot of different data. And there to compute a gradient with respect to FI would need to go through all the data. And there it's oftentimes people sample from the data and use stochastic gradient. So there the costly component is the computation. Okay, so you don't want to take too many gradient steps because every time you take a gradient step, you have to sample the data and can be costly. Whereas communication can be reasonable because they may actually have hardware connected to a shared memory, so they can just access the memory really quickly, read and write to it. Okay, so all right, so I just mentioned a bunch of different hardware scenarios, right? And we want to design a method that, depending on what the hardware needs are, can adapt. Like either trade off more communication to less computation or vice versa. Okay, so that's what we mean by flexible. Okay, and the robust, the method should be resilient against noises. So we were talking with again the hardware engineer who tells you, well, don't expect the robots have perfect communication amongst themselves, right? The signal may bounce off certain object and get lost, for instance. Okay, so there could be noisy, and there could be communication or computation errors. You can have packet loss. Things can be asynchronous. It's very hard to have all the robots running on the same clock, etc. Okay, so the method should also be robust against all these potential failures. Okay, so that's what the second keyword means. Okay? So we want to develop a class of methods that can be flexible and also somewhat robust against these potential failures. All right. And then, so that's going to be our overarching goal. And for the rest of the talk, I will present you two kinds of methods that one of them is very flexible. The other one is flexible and also robust. And we will evaluate these methods in this new cost framework. Okay. So A and B are some constant depending on the hardware. And the true cost of the algorithm is going to be the cost of communication times number of communication plus cost of computation times number of computation. Okay? And if, for instance, your methods, what you care is actually the speed, then we can set A equal to B and just, or maybe you just care about the computation. You can just set A equal to 0, only look at B, and that typically gives you a count of how many iterations you have. Okay? So this generalizes what people usually use to evaluate performance of the algorithm, okay, more than time. All right, and then we're going to provide convergence guarantees. Okay, so let's go ahead and get started. the first class. Okay, so the first class of method is motivated by the distributed gradient descent. We're just talking about that has a gradient step and communication step per iteration, and also the augmented Lagrangian based ADMM method that has a minimization per iteration, right? So, so I'm going to reformulate the problem with slightly easier notation. So lambda is my dual multiplier, A is the matrix representing the constraints. Okay, and then I also will introduce this B matrix here, which essentially you can think about this term as the penalty term. It penalizes for constraint violation, same as the regular augmented Lagrangian. So B is the positive semi-definite matrix, has the same null space as A, and the special case would be A squared. So that's exactly the quadratic penalty. Or it can take other forms. So we want to keep this in a general form. Okay, that's why we introduced another matrix here. It can be a weighted version of the graph Laplacian. Okay. So what are we going to do? We're going to take this augmented Lagrangian and say, hey, there are two extreme kind of method in the sense that one of them does one gradient and one communication per iteration. The other one does the minimization step per iteration, right? So can we design something in between? Meaning, why should we stick with either one gradient or infinitely many of gradient to get the minimization? Could we go somewhere in between, like have two gradients or three gradients or four gradients, and depending on how flexible or how many gradients the hardware would be able to do, we should be able to fill in the gap in between. Okay? And so we can. So that's where we started, and we said let's look at the augmented Lagrangian, right? And let's write out the regular primal dual update. So this is just taking one gradient with respect to the primal variable and one gradient step with respect to the dual variable. Okay, so you can write this, and there are lots of methods have similar forms to this, such as extra digging. They have linear convergence guarantees, but the ADMM also is linear, but numerically speaking, ADMM, the one with minimization, is still faster. Okay, so fine. So now we pose the question, right? Can we have multiple updates? Okay, so in particular, we can think about this extra digging type of methods as one primal, one dual, whereas the ADMM has many primal and one dual. So both of these share the one dual part. So we're going to keep that and then say, let's try to see how many primal updates we can have in between. Okay, so let's try have multiple primal updates. Would that be helpful to improve the methods? Okay, and then if you look at the primal update here, right? Oops, sorry. You would need to recompute the gradient. And so this term right here. So first term is just local information. This term is based on the dual multipliers. You only have to compute it once. But the last term here, B of x, so remember B is related to the matrix A, the adjacency matrix. Essentially, every time you compute B times x, you need to communicate with your neighbors. And if x is updating, so this B of bxk term would need to be recomputed every time. So if we run multiple primal updates, then we should recompute primal gradient and recommunicate. Okay, but is that really necessary, or is that efficient? Okay, so that's question number 2. All right, and turns out the answer is no to neither of these. Okay, so then we introduce our methods here called FlexPD, flexible primal dual method, that essentially says we don't actually have to do any of the things before, meaning we don't have to recompute or recommunicate the gradient, recompute the gradient or recommunicate the iterates. Also, we are not required to do either one or infinitely many gradient updates. We can do any number of gradient primal steps. Okay, so that's what this FlexPD method says. So we start with the FlexPDF, this is the full version where we do update the gradient and we communicate that every single time. Okay. So that's what we call FlexPDF, and we have convergence guarantee for all these three different variations. Okay, and the second variation is FlexPDC, the communication version, where this is useful for the cases where communication is cheap but computation is costly. Okay, so we don't want to recompute the gradient every single time. We want to reuse the gradient. So we have outer iteration over k and the inner iteration over t. And in the inner iteration, we're just going to keep the old x at the beginning of the inner loop. So we are not going to recompute the gradient, but we're going to recommunicate with the neighbor. Okay. And then the last version is FlexPDG. The G stands for gradient. So here we update the gradient, but do not recommunicate with the neighbors at every time. So this is a case where computation is cheap, but communication is expensive. So there you just take a bunch of local steps recomputing the gradient without recommunicating with the neighbors. Okay. And then after T inner iterations, we're going to jump out and do a dual update. Okay, so this is what we call FlexPD method, and this is a picture illustrating what's happening locally. So let's say node 2 is update so this is, so far we're talking about synchronous implementation. So node 2 is updating and it's hearing information from its neighbors 1, 5, and 3. And in the full version, it will update the gradient using local information, and then this turn use the information communicated from the neighbors. Okay, and then so after if updates xi, it's going to send the updated version to the neighbors, and then they iterate this t times, and then they can work on the dual update. So every dual variable is associated with an edge. Okay? And then just iterate this to get the entire algorithm. Okay, and similarly, we have the C version where we just recommunicate but not recompute, or the G version where we just recompute the gradient but not recommunicate. So this illustrates this method, the FlexPD family can be implemented in a distributed way. So all you have to do is to update local information and communicate with local neighbors, or communicate with local neighbors. Okay. All right. So let me quickly go through another class of methods. Okay. So here, this method is flexible but also robust. So the FlexPD family, we have not had chance to analyze how robust it is yet, but we believe it is pretty robust. This one, we have all the analysis worked out for the resiliency part. Okay, so this is a NearDGD method. So DGD is a distributed gradient descent, and we call it NearDGD because it was motivated from DGD. Okay, except remember, we want the method to be flexible, right? The distributed gradient descent says I have to run exactly one consensus and one communication per iteration. This one says, let's break up the two components, the communication and the computation. So this is the communication part, and this is the computation part. So W, again, is the consensus matrix, W times Y, meaning you're going to take a weighted average with your neighbors. Okay, so let's separate these two, and then this W to the T to the K means we can repeat the communication T times before I do a gradient calculation. Okay? And similarly, you can take multiple gradient steps before you go back to communicating with neighbors. Okay? So this is what we call the NearDGD method, where the two components are the communication computation are separated, and the algorithm or the hardware can tell us how to customize this algorithm in terms of how many computation versus communication steps we can afford. And we have some nice guarantees for these. So as long as your communication step goes to infinity, then you get a linear convergence for linear exact convergence. Okay? And if you're in the case you don't care about exact convergence, reaching error neighborhood is good enough, then you don't have to move this communication to infinity. You can actually do a bunch of local gradient computations and then do one communication and just kind of repeat that process as well. So depending on the accuracy requirement. Okay, and the key that I'm going to present here is the stochastic version of the method, right? So the method is already flexible because we have decoupled the communication and computation. Now, once we have stochasticity, we're going to tolerate two kinds of stochasticity here. One is the error in computation. We're going to model that with a stochastic gradient. Okay, this is a typical representation where we cannot compute exact gradient. We're going to sample. Okay, and also we are going to talk about a communication error. So this could be actual error from packet drops, or this could be from quantization. So oftentimes we assume we can communicate the real numbers around, right? But in any kind of real world setting, things are digitized and there is no infinite precision communication. You would have to quantize the variable you communicate at some point. So there's going to be a quantization error here. Okay. All right, so that's what this TC is modeling communication error. Okay. So you might think this is very trivial, right? We're just throwing a bunch of very small errors in either the gradient or the communication. You should just be able to run your old method and it should work. That's what we thought in the beginning. We thought this is going to be very straightforward, just throwing all these errors, and then by law of large numbers or central limit theorem, things would just work out. Turns out that's not the case. Okay, so attempt number one is so remember this is solving generalizing the NearDGD, which has a communication step and a computation step. So the trouble comes really from the communication step. Okay, so let's try to just communicate as usual, but so take a weighted average of the neighborhood, but instead of the exact axis, we're going to use the quantized version or the arrow version. Okay, so this Q is the inexact version, the X is the exact version. So at next iteration, let's say I'm just going to do W times Q. Okay. Right, this would be the first thing we try because now we receive a noisy version, so we're going to use that. And turns out this does not work. The arrow, for our method, it's okay. The arrow doesn't blow up too badly. But if we do this kind of quantization on other methods, such as extra digging, the arrow from quantization really accumulates and blows up. So the iterate becomes unstable. All right, fine. Let's try attempt number two. Okay, so now we start getting serious, right? So for our method, the NearDGD method, if we do this kind of update, it works, but the error neighborhood becomes really large. Right? So once you have all these stochastic errors, you don't expect exact convergence. It will converge to error neighborhood. So for our method, it still converges, but to a relatively large error neighborhood. So let's try to improve it. Well, this naive update number one says we're going to use quantized version for all of my neighbors and myself. So there's really no need to use a quantized version for my own update because I know what it is, right? I'm not communicating with anybody else for my own update. I should just be able to use my exact update here, okay? So this one just says, I'm still going to take a weighted average with neighbors, but for all the neighbors, I'm going to use a quantized value. For my own, I will use the exact value. So this is slightly better than the previous one because in one term, I have the exact value. Okay. And turns out the same thing as before. As the naive attempt number one, the error still accumulates for some of the other methods. And for us, again, we have a relatively large error neighborhoods. Better than the attempt number one, but it's still pretty large, the error neighborhood in the analysis. Okay, so then we work really hard. We sample a bunch of literature, and then we get inspired to do this kind of update. Okay. What does it do? It adds an error correction term. And this is the correction term. So this is kind of related to the way extra was written. There's a correction term. So we're going to use quantized version for everybody, except at i's node, I'm going to correct for the error between x and q. So this q, so the notation can be confusing, but this q value right here is a quantized version of this x right here. And so even though it's j minus 1, j is the same iteration there. So I'm just going to subtract the error between the quantized one and the unquantized one. Okay? And so you might be curious about why we have to do this, right? well, I mean, for one, this works. So we can get a much smaller error neighborhood, and all the methods seem to stabilize with this kind of error correction. So 2 is my intuition on why we have this term. So because we're using Q instead of X, right? And this W is stochastic. So in the entire neighborhood, I'm going to introduce an arrow of the size Q minus X, right? If you look at it over the entire network. So by having this X minus Q term here at this ICE agent, I'm correcting for the arrow. And by doing that, I somehow on the overall level managed to cancel out the arrows and stabilize the system. Okay. So that's the lesson we learned from going through this exercise. It's not very trivial to deal with communication errors. You have to be careful how you correct for it. Okay. And then, as promised, we have convergence guarantees. I'm going to breeze through these. So we have convergence guarantees for FlexF, FlexPD, F, G, and C. All of these look like a linear rate. And then we also have convergence guarantee for the stochastic version of the NearDGD, the second method we talked about. Okay, and with all the arrows there. So something maybe interesting there is, so it has 3 terms, right? The first term is the linear term. So if there's no arrow, then you have just the linear convergence part. The second and third term are 2 arrow terms. The red term represents the network-related arrow because the beta is the second largest eigenvalue related to the graph Laplacian. And the blue term is coming from the stochastic noise. Okay. All right, those are not surprising. What's surprising is we have a free parameter inside our analysis. Okay, so what I'm saying is specific to our analysis. We don't know if it's something inherent to the algorithm, but this is the best that we can show. So we have this free parameter that we can tune to trade off between the size of the network and the rate. So in some sense, in our analysis, we can either get a relatively fast convergence rate but a worse error neighborhood, or a relatively small error neighborhood but a worse convergence rate. Okay, so we've noticed the other literature also have the same kind of observation as we did, but this is something on the upper bound of the speed of convergence. So we don't know if it's inherent to the algorithm or just a weakness of the analysis, but we thought it was interesting, right? So as the term approaches 0, the term in green and blue, so the linear term and the second noisy term, approaches the best case scenario in centralized case, but the red term related to topology blows up. All right, so lastly, let me just show you some quick simulations. Okay, so again, we have 2 classes of methods, FlexPD. So here we simulated a bunch of different variations. And one thing that might be on your mind is, hey, you just told us you have proof for any t, right? Any number of primal updates. So what exactly should I use for my application? Well, it depends on your hardware, but simulation shows if there is a big improvement going from 1 primal, 1 dual to 2 primal, 2 dual. Okay, and then slightly small improvement going from 2 to 3. Okay, so we think the sweet spot is somewhere between 2 and 3, and going from 3 to 4, the improvement is very minimal. Okay, and it also depends on how costly it is to run your update. And we showed these 3 plots evaluated on different x-axis, so total iterations, total number of communication, total number of gradient evaluation, and you can see depending on how we evaluate the algorithms, different versions going to perform differently, because obviously the one re-evaluating gradient is going to accumulate a lot of cost if gradients are costly. Okay. All right. And then you can also run the same kind of simulation over for NearDGD, the stochastic version. And I just want to show you on the left-hand side, these are different ways to account for the error. So the ones on the bottom are the last approach we presented. This is the one with the error correction. And you might be, maybe it's not believable when I say, the naive attempt doesn't work, right? So I'm going to show you some figure right here. You can see the other groups, the error for some methods, it does really blow up if you don't do the error correction carefully. Okay, so my time is up. I'm going to conclude and say we presented a class of flexible and robust optimization algorithms that can be adaptive to hardware capabilities. Okay, I'm going to stop here, maybe leave a minute or two for questions. Okay, thank you.
Okay, thank you. I mean, any questions?
Yeah, can I ask a question?
Sure.
Yeah.
I know in some network there exists the hub, which means that the hub is a super user that connects with many other users.
Mm-hmm.
So I'm curious, is your optimization algorithm also works for the network with hubs?
Okay, so it depends on which ones you have. I guess the short answer is yes. We're not assuming anything special about the network topology. As long as it's connected network, it applies. Then the other thing is, by hub, if you mean a star graph, like the federated learning example I've shown before, then there exist other methods that takes advantage of that particular structure. So it's probably better to use specialized algorithm. But if you're talking about hub and spoke, like there are lots of different hubs throughout the network, kind of like the airlines routing map. So in that case, our method works, and the topology effect will be captured in the in these parameters, the beta term. Oops, sorry. This term right here, the beta would be different depending on if you have a hub or not, depending on the connectivity of the graph, essentially.
Okay, I see.
Other questions? Okay, actually, I have a few questions, but maybe I can ask you later.
Sure.
Yeah, I don't want to hold others here.
Of course, yeah.
Yeah. Okay, let's thank Hongmin for the nice talk. Yeah, thank you.
Yeah, thanks for the invitation.